Hi guys, okay, this video is going to be a little longer than most because we want to check each component within the system and how we're going to be testing it. I now have 2 meters the same. Went and bought 2 sets of leads that are identical, zero loss leads or something they're called, and indeed if I switch these to ohms and hook the leads together, it comes up with 0. So here we have another meter, and that is going to be used to measure the resistance across the milliamp shunt in each meter, which is what we will be using to measure input and output. And then we will be measuring the voltage with our scope across this shunt, both on the input and the output. And of course these 2 meters will tell us the current draw and the current output of the input and output of the system. So I have soldered a little pin here and here, which is the positive input to the system. That will be where we're placing our input meter. And we have 2 pins here, which is the output of the system and the input to the LEDs. The scope at the moment is set on 20 millivolts at 1 microsecond for our time divisions, and as you can see the line is a little bit wavy, and that is because at that resolution in millivolts it will pick up anything simply by touching the probe. We can get all sorts of strange readings, and that's purely because of its sensitivity. If we turn it down, of course the line straightens out, and that is on 0.2 of a volt. But because we're on such a low input voltage and output voltage, and we're measuring across a low ohm shunt, we're going to be using the 20 millivolts to measure the voltage across that shunt. This meter here, as I said, we're going to use to check the resistance in these shunts to make sure they're the same. First we check the resistance in these leads themselves, and you can see we have about 0.8 or 0.9 of an ohm resistance there, so that would have to be subtracted from the amount we get from each one of these. So we'll now hook up to the meter that is on your left. And you'll see we've got 330 microamps there. That is because that's how the meters work. They send out a certain amount of voltage or current and measure the voltage drop and calculate the resistance. So you can see we got about 2.2 to 2.3 ohms minus our 0.8, and that will give us about 1.4 ohms across that resistive shunt. And we will also measure the other one, of course, to make sure that is the same. So we're now measuring the resistance across this shunt, and as you can see on this meter here, it is the same. So we have 2 identical meters that are reading 2 identical resistances. So we no longer need that meter. We'll chuck that away. So the next thing we're going to do is make sure that our solar panel is not adding to the system via the ambient light. And we can simply see if there's any current coming off each side of the solar panel by hooking up one of our meters. And as you can see, we don't even have 10 microamps, and there's nothing coming off of that solar panel, and that also indicates the solar panel is not hooked directly to the battery. So now that we've sorted that out, I'm going to hook the right hand meter to the output, and the meter that is on the left is going to be hooked to the input. When we do this, you can see our LEDs come on. So we have about 780 microamps on our input at our battery voltage, which is about 1.2. That doesn't really matter because we're going to be measuring the voltage across each resistive shunt via our scope. Our output is about 480 milliamps. Now you may think that that is less than the input, but as you'll see, the voltage is higher, as it would have to be driving the LEDs in the first place. So now we're going to hook the scope across our input shunt, and as you can see, there is our input pulses. Now, something I'm going to show you about these pulses a little later on, both on the input and the output. So that is across our shunt, our resistive shunt on the input meter, and I will get a close-up of the scope so you can take a screenshot of both the input and the output and compare them. Okay, so now we'll go to the output, and it is zeroed, as you can see. So we'll now remove the scope from the output, the input, and we'll place it onto the output. And there is our output. So what I'll do now is I'll zoom the camera in, and it's got autofocus, so I'm hoping it's going to keep its focus. I have a bit of trouble with that. It's got no manual override. Okay, clear enough. Okay, so that's our input side. The meters are beeping because they're going to time out. I'll show you something a little interesting on what you see as being each pulse. Like I said, at the moment we are on 1 millisecond, and there's a pulse in each division, just about, so it would be somewhere around what looks to be 1000 Hertz or 1 kilohertz. But if we go up on our time divisions, we'll start to see something interesting, and that is each pulse, what looks to be each pulse, is actually a series of pulses and a ring on the end. And if we have a closer look at them, it starts to get really messy. And you can see a ringing at the beginning of each pulse. We are now set on 1 microsecond per time division, so we're still well within the scope's range, and that is 0.5 of a microsecond, and the scope does go down to 0.1 of a microsecond, and on 0.2 of a microsecond you can see a definite ring on each pulse. So it looks like absolute chaos, but as you can see, what you're seeing back here as being a pulse is actually a whole lot of pulses, about 10 pulses instead of just the one. Now just keep that in mind, we have about 10 pulses on each one of these things that look like pulses. Now the output side of it is exactly the same. So I'll put the scope back onto the output. As you can see, it looks like a nice clean pulse, and then a fairly high current drop off. And yes, we are still set. That is our 0 volt line, and that is the voltage across this shunt resistor. But as you will see, once again, it is a series of pulses that looks identical to the input, other than we have a few more spikes. And here you can see a lot more. So now the other thing I want to show you is what the solar panel is actually doing. So I'm just going to hook the scope across the solar panel itself. Turn the voltage down. Now what you can see here, it's very hard to keep this stable. That was the chicken wire thing I was talking about, TK, but I was just looking at the scope wrong. This is in fact what we have. And what you can see here is about 10 pulses of the LEDs building up the voltage across the cell, and then the cell drops off. And that was why I was telling you to keep note of the 10 small pulses within each pulse of the circuit, because we have 10 flashes of the LED, and I think that's why we were getting that other effect. The 10 pulses within each pulse, what looked to be each pulse, is actually the LED firing, and each time the LEDs fire you can see each dot is the current from the LEDs being sent through the solar panel, and it's just like tapping the voltage up in the solar panel and until it gets to its peak voltage, and then it drops down and starts again. So for a very simple little circuit, hooking it up like this, having the LEDs pulsing the solar panel, and the solar panel switching the little IC on and off, certainly has some interesting effects. So once more, I'll show you the input. Turn it back up to 20. So there's the input side across this shunt. And that is the output side across this shunt. So as you can see, we have a lot higher voltage and a big current curve until it drops down to, I'm assuming, the voltage of the battery. So battery voltage seems to keep the circuit supplied with a certain amount of voltage, and the combination of the solar panel, the pulses and the inductor lift that voltage up, and then we get a big current that drops down over the period of each pulse from the solar panel itself. Now the one other thing we're going to check, and it wouldn't have made much difference because we're using the meter both on the input and the output, and then the scope, sorry, is that the scope itself is not adding any power to the system. So I now have it hooked up to here. Once again we have nothing there. So that's where we're at the moment. I'm not sure with the equipment that I've got. It's only a single channel scope. I'm going to have to put up with it until I can afford to get a dual channel scope. But as you can clearly see, the input voltage and the output voltage are far different across both our meters. We will in fact right now swap the meters over. We'll put the left meter on the output just to double check, and we'll put the right meter here onto the input. That's the scope probe bleed. Try the meter in. Bleed looks and works better. Once Again, put the scope across the input. And now we'll put the scope across the output. So as you can see, the meters are in no way playing a part, and that's a very good indication that they are fairly well calibrated. Alright, that's it from me for now. So what we need probably is a couple of replications, maybe someone with a dual channel scope that can do the same sort of test, and we can look at both the input and the output at the same time rather than having to change it around. Okay guys, we'll have fun with it, and I guess next, once we've worked this little part of the system out, we're going to go on to the second part, but this part is looking very good at the moment, so let's hear your thoughts on it, and talk to you soon.